Well, welcome back to the next lesson or the second lesson in our study of the network layer as part of the course Networks and Distributed Systems. This course is based on the textbook by Jim Couros and Keith Ross, Computer Networking, a Top-Down Approach. We are examining the subject based upon the TCP/IP model of networking. There are a number of modules in this course, and we have already covered the first three: an introduction, a module on the application layer, a module on the transport layer, and now we are into the second lesson of our module on the network layer. So let's pick up where we left off. We just said that the network layer has two important functions: forwarding and routing. But we'll soon see that in some computer networks there is a third important network layer function: connection setup. You remember from our study of TCP that a three-way handshake is required before data can flow from sender to receiver? This allows the sender and receiver to set up the needed state information, such as sequence numbers and initial flow control window size and so forth. Some network layer architectures, like ATM, frame relay, and others, require the routers along the chosen path from source to destination to handshake with each other in order to set up state before network layer data packets within a given source to destination connection can begin to flow. In the network layer, this process is referred to as connection setup. Let's consider different types of services that might be offered by the network layer. When the transport layer at a sending host transmits a packet into the network, can the transport layer rely on the network layer to deliver the packet to the destination? When multiple packets are sent, will they be delivered to the transport layer on the receiving host in the order in which they were sent? Will the amount of time between the sending of two sequential packet transmissions be the same as the amount of time between the reception? Will the network provide any feedback about congestion in the network? What are the properties of the channel connecting the transport layer to the sending and receiving hosts? The answers to these questions and others are determined by the service model provided by the network layer. The network service model defines the characteristics of end-to-end transport of packets between sending and receiving systems. Now consider some possible services that the network layer could provide. In the sending host, when the transport layer passes a packet to the network layer, specific services that could be provided by the network layer include guaranteed delivery. This service guarantees that the packet will eventually arrive at the destination. Guaranteed delivery with bounded delay. Bounded delay is a term used to describe a network in which the total delay experienced by data traversing the network can be guaranteed not to exceed some predetermined values. Make a note of that. Bounded delay is a term used to describe a network in which the total delay experienced by data traversing the network can be guaranteed not to exceed some predetermined value. Furthermore, the following services could be provided to a flow of packets between a given source and a destination, such as in-order packet delivery. This service guarantees that packets arrive at the destination in the order that they were sent. Guaranteed minimal bandwidth. This network layer service emulates the behavior of a transmission link of a specified bit rate between sending and receiving hosts. As long as the sending host transmits bits as part of packets at a rate below the specified bit rate, then no packet is lost and each packet arrives within a pre-specified host-to-host delay. Guaranteed maximum jitter. This service guarantees that the amount of time between the transmission of two successive packets at the sender is equal to the amount of time between the receipt at the destination, or that this spacing changes by no more than some specified value. Security services. Using a secret session key known only by the source and destination host, the network layer in the source host could encrypt the payloads of all datagrams being sent to the destination host. The network layer in the destination host would then be responsible for decrypting the payloads. With such a service, confidentiality would be provided to all transport layer segments, that's TCP and UDP, between the source and the destination host. In addition to confidentiality, the network layer could provide data integrity and source authentication services. This is only a partial list of services that a network layer could provide. There are countless variations possible. That sounds really nice, doesn't it? It sounds like the kind of service that Transport Layer provided. All that said, the Internet's network layer provides a single service known as best effort service. In other words, it does none of that stuff. With best effort service, timing between packets is not guaranteed to be preserved. Packets are not guaranteed to be received in order that they were sent, nor is the eventual delivery of a transmitted packet guaranteed. Given this definition, a network that delivered no packets to the destination would satisfy the definition of best effort delivery service. Other network architectures, other than that used by the Internet, have defined and implemented service models that go way beyond the Internet's best effort service. For example, the ATM network architecture provides for multiple service models, meaning that different connections can be provided with different classes of service within the same network. The point here is only to note that alternatives do exist to the Internet's best effort model. Two of the more important ATM service models are constant bitrate and available bitrate service. The constant bitrate ATM network service was the first ATM service model to be standardized, reflecting early interest by the telephone companies in ATM and the suitability of constant bitrate service for carrying real-time constant bitrate audio and video traffic. The goal of constant bitrate service is conceptually simple: to provide a flow of packets, which are known as cells in ATM terminology, with a virtual pipe whose properties are the same as if a dedicated fixed bandwidth transmission link existed between sending and receiving hosts. With constant bitrate service, the flow of ATM cells is carried across the network in such a way that a cell's end-to-end delay, the variability in the cell's end-to-end delay, and the fraction of cells lost or delivered late are all guaranteed to be less than specified values. These values are agreed upon by the sending host and the ATM network when the constant bitrate connection is first established. With the Internet offering so-called best effort service, ATM's available bitrate ATM network service might best be characterized as being slightly better than best effort service. As with the Internet service model, cells may be lost with the available bitrate service. Unlike the Internet, however, cells cannot be reordered even though they may be lost. And a minimum cell transmission rate is guaranteed to a connection using available bitrate service. If the network has enough free resources at a given time, a sender may be able to send cells successfully at a higher rate than a minimum cell transmission rate. Additionally, ATM's abbreviated bitrate service can provide feedback to the sender in terms of a congestion notification bit or an explicit rate at which to send that controls how the sender adjusts its rate between the minimum constant rate and the available peak cell rate. In the last module, we learned that a transport layer can offer applications connectionless service or connection-oriented service between two processes. For example, the Internet's transport layer provides each application a choice between two services, UDP, a connectionless service, or TCP, a connection-oriented service. Now, you're an expert on those now, right? In a similar manner, a network layer can provide connectionless service or connection service between two hosts. Network layer connection and connectionless services in many ways parallel transport layer connection-oriented and connectionless services. For example, a network layer connection service begins with handshaking between the source and the destination hosts. And a network layer connectionless service does not have any handshaking preliminaries. Although the network layer connection and connectionless services have some parallels with transport layer connection-oriented and connectionless services, there are crucial differences. In the network layer, these services are host-to-host services provided by the network layer for the transport layer. In the transport layer, these services are process-to-process services provided by the transport layer for the application layer. In all major computer network architectures to date, that's Internet, ATM, frame relay, and so on, the network layer provides either a host-to-host connectionless service or a host-to-host connection service, but not both. Computer networks that provide only a connection service with the network layer are called virtual circuit networks. Computer networks that provide only a connectionless service at the network layer are called datagram networks. Remember those two terms, virtual circuit networks and datagram networks. The implementations of connection-oriented service in the transport layer and the connection service in the network layer are fundamentally different. We saw in the previous module that the transport layer connection-oriented service is implemented at the edge of the network in the end systems. We'll soon see that the network layer connection service is implemented in the routers in the network core, as well as the end systems. In other words, the connection-oriented service in the transport layer is between two end systems, ignoring the various other routers along the path, while the connection-oriented service of the network layer is between each of those routers along the path, including the routers at the end. Virtual circuits and datagram networks are two fundamental classes of computer networks. They use very different information in making their forwarding decisions. Now we're about to explore these two classes of computer networks, starting with virtual circuits. Before we start, why don't we take a break right here so that you can review your notes on this lesson and update your study guide. And when you're prepared, come on back and we'll get started on virtual circuits.